Hello my friends, this is about torque and static equilibrium. We already learned about torque, we already learned about equilibrium before, where we said total force should be zero. Actually, that's when we assume an object is a point particle. If we have an extended object like this square here, for it to be in total equilibrium, it should have linear equilibrium, if you like, and rotational equilibrium, meaning for it to be in linear equilibrium, it should have total forces on it to be zero, which is the case here. F to the right, F to the left cancels each other. For it to be in rotational equilibrium, it should not rotate. Here we have forces still canceling each other, but each force will rotate it in the same direction, so this square here will rotate. So it's in linear equilibrium, if you like, but rotational equilibrium, no, it will rotate and then come into equilibrium a bit later. So for total equilibrium to happen, actually there are two conditions for extended objects. One, total net force should be zero, or total force should be zero, and net torque or total torque should be zero. It should not be rotating and it should not be moving or rotating or moving with a constant velocity, remember? So here is the situation for a total static equilibrium for an extended object. Zero net force, meaning total Fx is zero, up forces cancels down forces, right forces cancels up left forces. Total Fy zero, up forces cancels down forces. Total torque zero. Torques, the forces that rotates to clockwise cancels those that rotates counterclockwise, or clockwise torques cancels counterclockwise torques. Remember, torque is the rotational effect of a force. A quick question: which of the objects is in total static equilibrium? This is not. A is not, because we have 2F to the right, 1F to the left. First of all, F net is not zero. I don't even have to look at the rotational equilibrium. It's not an equilibrium. This guy is also the same, 2F to the right, 1F to the left. So F net is not zero. The third one has 2F to the right and a larger force, which is about 2F to the left. So F net is zero. But if I look at and imagine the rotation, this object would rotate in this direction because these two forces would be tempted to rotate in this direction, which is counterclockwise. The third one clockwise, but the counterclockwise would win. So total torque is not zero, so it's not an equilibrium. If I look at this guy, however, 2F to the right, 2F to the left, so F net is zero. I can easily logically see that the rotational effects would also cancel each other. Here this guy will be applying a less torque here, and this guy will still be rotating. I'm thinking in terms of rotating it around this point. If I think in terms of rotating it around the center, this guy would apply no torque. These two torques cancels, and each way it's easy to see logically that total torque is also zero. So it's an equilibrium. For rotational equilibrium, now we'll focus on this more because we kind of know the linear equilibrium. Total forces should be zero, so up forces should cancel down forces, right forces should cancel left forces. That will come up in some questions as well, but main focus now will be total torque is zero, rotational equilibrium. And this question is a very nice one involving that. A capstan is a device used on old sail ships to raise the anchor. A sailor pushes the long lever, turning the capstan and winding up an anchor rope. Here is the picture of the situation. So we don't have to draw an ugly picture. There is a very nice picture for us again. The rope tension due to the weight of the anchor is 1500 Newton. So this guy is given to us. There's an old picture here showing how this was applied. There are many sailors pushing it here. The distance from the axis to the point of lever, this would be the axis here. The guy is pushing on the lever here, and the rope is going around the axis here. So we are lifting up the anchor. So the distance from the axis to the point on the lever where the sailor pushes is 7 times the radius of the capstan. So if this is the radius of the capstan, or distance from the center axis to the point where the sailor pushes is 7 times that. I can go ahead and give this a value to solve this problem. I can leave it as r because it will cancel. So let's call this 1 meters. Then this will be 7 meters. Since they are a ratio, I can safely do this in this case. With what force must the sailor push in order to turn capstan at a constant speed? That tells me there's rotational equilibrium here. If there's constant speed, tau net is 0. And the speed we're talking about here is actually rotational or angular speed. We won't be really, we call it omega, angular speed, really covering calculations and so on about it, but idea is going to be there. So angular speed is constant means, or rotational speed is constant means we have net torque 0. So what do we have here? We're going to look at the rotation of each forces. We're going to decide which direction they are rotating, and we're going to give the torques plus minus signs, and then we'll say plus torques. Total adds are equal to minus torques, or counterclockwise torques, which is generally traditionally taken to be plus, are equal to clockwise torques. I generally am tempted to drop plus minus, just say clockwise, counterclockwise. Pivot point is important. Pivot point naturally would be the axle here, center of rotation, right? So this is our pivot, and I'm going to look at which direction each force would rotate with respect to this pivot. Tension would rotate counterclockwise, and the sailor would rotate clockwise. So tension would apply a positive torque, and sailor would apply a negative torque. Then I write down my rotational equilibrium equation. I want you folks to get used to using counterclockwise torques are equal to clockwise torques. We have 2 only here, right? If there was more, we would add all the counterclockwise torques, and they would be equal to added all the clockwise torques. But we have 1. Counterclockwise torque is the torque of sailor, and the clockwise torque is the torque of sailor. Counterclockwise torque is the torque of the tension that the rope connects to the anchor. So we calculate those. The torque of sailor would be the force the sailor applies times the distance to the axis point, which is, we took as 7 meters. I put 7r here. So with r we replace 1 meters. Times the angle, sine of the angle between r and force. Remember, but in this case we have 90 degrees for both. So it doesn't matter, it will be 1. Sine 90 is 1. We can drop it. I put it here to help you folks get used to the idea that sine 90 is 1. So if we have 90 degree, we can drop sine 90, or we can say f perpendicular is already, f is totally perpendicular, so we can just go f times the distance. So we have for the sailor f times 7r times sine 90. For the tension, we have tension times r times sine 90. Each again is 1. From now on, I'm going to drop them. We have perpendicular forces already perpendicular to r. Then we solve for f. We know the tension, r goes away. We'll have f is equal to tension over 7. And we'll solve for it to find it 210 Newton. I can go by logic here as well. If I'm applying my force 7 times farther away and applies the same torque, that means it's 7 times smaller than the tension. Choosing the pivot point is important. We can choose any point to be a pivot point, although generally there is a natural pivot point. But as you're solving problems, choose any point that is you think is the most appropriate and easier way to solve your problem. For example, if I'm calculating NA and B and weight related questions involving this hammer here, I can choose point A and look at torques. Then weight would be rotating clockwise, and NB would be rotating counterclockwise. And there are only two if the hammer is in equilibrium. Let's say I'm holding the hammer here and I'm using this as my pivot point, or I put the hammer somewhere here. If it's in equilibrium, that means counterclockwise torques equals to clockwise torques, and so on. If I choose point B to be my pivot, I can still solve. Let's say I'm not interested in finding NB, but I want to find NA, then I would choose point B to be my pivot point. Then with respect to point B, the weight would rotate in this direction. I have to go by logic to decide that. So with pivot point, the rotation direction, that's the direction of torque changes. Now weight would rotate clockwise, and NA would rotate, weight would rotate counterclockwise, that's counterclockwise, and NA rotates clockwise. And then I apply the same. Equilibrium clockwise torques are equal to counterclockwise torques. This here nicely summarizes what to do. Generally, we go the same steps. We strategize. That means draw an ugly picture, decide on what is happening, decide on a pivot point, and think about how you would calculate your question. Prepare for solutions, show all the known and unknown, show all the forces, and so on, and then solve. As we solve, we'll use two simple equations. If system is in equilibrium, F net is 0, torque net is 0. In this picture here, I would naturally assume that this would be my pivot point. Weight is rotating then in this direction, tension is rotating in that direction. But again, here too, I can pick any point to be my pivot point. Here is an example. It says use our reasoning to solve it, and its reasoning would be easy here. I hang 1,000 Newton weight here. It's pulling in this direction. There is a distance to scale. If I call this R, on this side I have the same distance, and there is a force on this side here. I can directly go ahead and say if they are the same distance, they should have the same torque canceling each other. System is in equilibrium because it's not rotating. Then we say this force should be also equal to 1,000 Newton because they're applied in the same direction, same distance, and they cancel each other's torques because there's no rotation here. This would be torque. Let's call it tau 1. It will be clockwise, negative. Again, I'll stick with clockwise. And this guy would be torque 2, counterclockwise. So it would be positive. Then when I apply clockwise torques are equal to counterclockwise torques, I say these two torques are equal because I have rotational equilibrium, right? Rotational equilibrium. How do I know there's no rotation? That's why. Alright, and when I apply F times R is equal to 1,000 times R, Newton times R, R's cancels. Again, I can give them a value here, but they will cancel anyways. F should be 1,000 Newton. This is for those who likes calculations. Now, what will the scale read? Those two forces are down. Of course, scale will apply an upward force here. And then to solve for the scale, I say F up is equal to F down. Again, the system is in equilibrium in both ways, linear and rotational, because it's not moving, it's not rotating, nothing is happening, right? Then I say F scale is equal to 2,000, added all those forces, which are 2. Very important point here, which I actually drew on. I'm gonna erase that, is that rod we assume to be massless. If there was a mass of the rod, then F scale should be also holding that. So we would add that in here. But it's massless. This is important here. So I'll put F scale on this side. So it's a simple question, but we can do a lot by thinking about it more. Alright, 2000 Newton is the force on the scale, or what the scale reads, which is the force. That's simply what is rotational equilibrium. Total torque is 0. Counterclockwise torques are equal to clockwise torques. And we'll do some applications now, some questions. And one very important application is finding the center of gravity. We already talked about center of gravity a little bit. I'm trying to pull this guy aside, but it doesn't like that. All right. Finding the center of gravity of irregular objects. We already talked about regular objects, center of gravity being in their geometrical center. We'll have that in some problems. In some other problems, it could be irregular objects, like the figure you see here. We actually solved the problem on an irregular object as well, without mentioning how we could find the center of gravity using torque. So now I want to mention that. If I have an irregular object, I can find the center of gravity by putting it on a pivot point where it balances. Means it's the center of gravity of that object. We mainly know this from our daily life. So if I hold this guy at this point and it is stable, not rotating, falling from my hand, that means it's in rotational equilibrium, right? And I know that will be its gravitational center of gravity. So it's in a rotational equilibrium. When I put it on a equilibrium, let me spell that. That means the pivot is on center of gravity. So I can find the center of gravity experimentally, just putting it on a pivot and then finding the point where it balances. What happens then, there is a weight on one side, another weight on the other side. Each rotates in different directions. Torque 2 here would be clockwise, right? Which is negative again. And torque 1 would be here, counterclockwise. And they would cancel each other because it's in equilibrium. Then we say torque 1 is equal to torque 2. So weight 1 times R1 is equal to weight 2 times R2. Notice here weight forces are perpendicular, so I am directly dropping sine 90 because it's 1. I'm used to it now. So knowing, let's say, omega 1, weight 1 R1 and R2, I can find weight 2. Or knowing weight 1, weight 2 and R1, I can find R2. Experimentally, also I can just put the system on a pivot point. When it balances, I can measure R1, R2 and say, okay, here is the center of mass. So total torque is 0 if we choose the center of gravity as the pivot point of the system. That's one important thing here. Another thing we can logically think that the center of gravity, if we have an irregular object, would be closer to the higher weight. Another important thing to get out of this is that. And if we put the system on a pivot where it balances, total torque is 0. So general idea is counterclockwise torques are equal to clockwise torques, which is the general idea of this lecture as well. Here's an example, and examples will be all similar sorts in this section. A 2-meter board weighing 50 Newton extends out over the edge of a table with 40% of the board's length of the table. So I'm gonna try to draw a table here, and we have a board on the table. I'm gonna try to that board. 40% of it off the table. The board weighs 50 Newton. One important thing here, actually, I should have said is we assume the board is uniform. So it's a regular object and mass is uniformly distributed. If it is not said, we will assume the board's mass is uniformly distributed. And the importance of that is that the mass, the weight of the board is in the center of it. Alright, that would be my mg, or the board's mg weight, which is given as 50 Newton. So I'm showing that in the center of the board. So the total length is 2 meters, and in the middle I would have this mass hanging. What is left? 1 meters. 1 meter. Now total length of the board is 2 meters. That's the total length, and 40% of it out of the table. This part is 40%, so I'm gonna decide how much is that by simply finding the 40% of 2 meters. To find that, we just multiply 2 meters by 40 over 100. You guys know that. So simply 2 times 0.4, that's 0.8 meters. So this part here, this little part here is 0.8 meters. So I did some walking around, imagining the situation. That's my preparation, strategizing and preparing for the solution. How far beyond the table edge can a 20 Newton cat walk before the board begins to tilt? So I'm looking for before the board begins to tilt means I'm looking for rotational equilibrium. So a cat will be walking to a point somewhere here, I don't know, and I'm gonna have weight of the cat, which is 25 Newton here, and I want the board not to tilt, meaning if I pick a pivot point, and naturally I will pick the edge of the table, because if the board tilts, it will be tilting from there, and apply for, if I don't want tilting, torque net about this pivot point should be 0. It's getting cluttered, but I'm gonna put here pivot. Okay, so I draw my picture, decided the distances, find my pivot point. I'm ready to solve. If I look at the rotation logically, the cat would rotate the board in this direction. I'm gonna call this torque 1. And it's clockwise, so it will be negative, but again I'm gonna go with clockwise equal to counterclockwise torques, and the weight of the board would be rotated in this direction, and this will be torque 2, tau 2, and it's counterclockwise positive. And I'm going to jump into saying torque net is 0. Clockwise torques are equal to counterclockwise torques, or positive torques are equal to negative torques. Then we don't put in the signs. Remember, just like we did with the forces, we say clockwise is equal to counterclockwise. Take everything as positive here. Clockwise, torque 1 equals to counterclockwise torque 2. Remember, again, we're not put in positive negative sign. That's already included in the idea of clockwise is equal to counterclockwise. We worked it out there already. And I am looking for this distance. I'm going to call it x. How far away from the pivot point should my cat stay? So we will have this equilibrium. I don't know that distance. I know the weight of the cat, and I can find the distance of the weight of the board to here. I know it's in the center, 1 meters here. This green part I calculated 0.8, so this distance of mg to the pivot point here is 0.2 meters. So I'm going to write down here then mg times 0.2 meters is equal to weight of the cat times x. I don't know that x. And I will solve for x by dividing each side by weight of the cat. So my x is equal to, this guy goes away, mg times 0.2 meters divided by weight of the cat. Well, I wrote really colorful here. Charming. Alright, what was mg? Weight of the board is 50 Newton, directly given, times 0.2 meters divided by 25 Newton. And I'm going to find here 0.4 meters. I could logically also go say 50 Newton will rotate in this direction 0.2 meters away, 25 Newton, half of that, should be put twice farther away so the board will not tip, right? Could it be closer? Yes, but maximum twice farther away. Alright, my friends, this question is for you. Read it, solve it. The answer should be 1.4 meters. You are given masses of two children here on a seesaw. You have mn times g on the side. So Emma and Noah playing seesaw. So me times g on this side. And the question is asking you if Noah should sit 1.6 meter away from the pivot point, how far away Emma should sit. So you're looking for the distance of Emma. Tau net is equal 0 for the seesaw to be in equilibrium or balance, right? Exactly balance means rotational equilibrium, not rotating. You have, I'll call this torque of Emma clockwise and torque of Noah counterclockwise. So this is positive, this is negative. Total torque is 0. Apply that and solve for xe. Again, we should be 1.41 meters. Logically, Noah is 22 kilogram, Emma is 25 kilogram. I could guess that Emma should be sitting a little closer. So that's like assessing our result. If I get a larger number, that means I made a mistake. The answer again is given here. But, so go ahead and solve it. Simply say clockwise torques are equal to counterclockwise torques. Don't include negativity again after you do this because we worked out negativity just like we did with the forces. That's skipping a step and going for an easy way. Alright, that's all, and we'll do some more examples in class. See you in class.